Assalamualaikum warahmatullahi taala wabarakatuh and good day to everyone. So today I will continue my lecture on chapter 5 Advanced Thermodynamics MME6154, the chapter 5 which is the energy and mass balance equation for control volume. As a recap, in chapter 4 we already learned the energy balance equation for closed system. Okay, so in the first two chapters we already understand the difference between closed system and open system. So in chapter 4, in previous chapter 4, we learned about the energy balance equation for closed system. However, in this chapter we will learn about the energy balance equation as well as mass balance equation for open system, or the other name is control volume. Why we have to learn about these two energy transfer and also the mass transfer? Because in open system both energy and mass can cross the boundary of a system. Okay, it is different with closed system where only energy can cross the boundary. Okay, in chapter 5, we will learn on the conservation of mass, okay, where we will see on the mass balance equation for a steady flow process and also mass balance equation for incompressible flow. So what is incompressible flow? Okay, I will explain in the later topic 5.1. And then we also will learn about flow work and the energy of a flowing fluid, okay, where energy transport by mass uh, will be presented. And then in 5.3 we will learn about energy analysis of steady flow system, and also I will explain a little bit on the some steady flow engineering devices that have been used widely used in engineering field, which are nozzles and diffusers, turbines and compressors, throttling valves, mixing chambers and heat exchangers, and also pipe and duct flow. Okay, so in chapter 5, the objective is to develop the conservation of mass principle, and then we will apply the conservation of mass principle to various systems, including steady and unsteady flow control volumes. Okay, control volumes means open system. Apply the first law of thermodynamics as the statement of the conservation of energy principle to control volume. Okay, we will identify the energy carried by a fluid stream crossing a control surface as the sum of internal energy, flow work, kinetic energy, potential energy of the fluid, and to relate the combination of the internal energy and the flow work to the property enthalpy. Okay, and then we will solve energy balance problems for common steady flow devices such as nozzle, compressors, turbines, throttling valves, mixers, heaters, and heat exchangers. Okay, and last we will apply the energy balance to general unsteady flow process with particular emphasis on the uniform flow process as the model for commonly encountered charging and discharging processes. Okay, let's start our lecture on the conservation of mass. Okay, conservation of mass. What is conservation of mass? You can see from this figure here, 2 kilogram of hydrogen plus 16 kilogram of oxygen will resulting on 18 kilogram of water. Okay, the conservation of mass principle is one of the most fundamental principles in nature. So this is the example of conservation of mass. Okay, when 2 kilogram of hydrogen reacts with 16 kilogram of oxygen, 18 kilogram of water is formed. Okay, so it is not 10 kilogram of water or 16 minus 2, 14 kilogram of water. It should be 2 kilogram hydrogen plus 16 kilogram oxygen equal to 18 kilogram of water. So in energy as of closed system that we learned in previous chapters, okay, the conservation of mass principle is implicitly used by requiring the mass of the system remain constant during process. Because in closed system, we understand that only energy can cross the system boundary. However, in open system or control volume, mass can cross the boundaries. So we must keep track of the amount of mass entering and leaving the control volume. So in this chapter 5, we have to understand that in order to calculate the total energy, okay, entering or leaving the system, and the total mass that entering or leaving the system, the open system, uh, we have to calculate, because these two can cross the system boundary. Okay, it is different with closed system where only energy can cross the system boundary. Okay, in previous chapter 4, okay, we learned about the energy balance equation where delta E equal to E in minus E out. Okay, so this energy transfer can be happen by two methods. First, from heat, and also another one is by work. Okay, and also we understand that in energy transfer, there will be macroscopic energy and also microscopic energy, where macroscopic energy associated with kinetic energy and potential energy. However, in microscopic energy, we have the internal energy. Okay, so now, the conservation of mass principle for a control volume. The net mass transfer to or from a control volume during a time interval delta t is equal to the net change, increase or decrease of the total mass within the control volume during delta t. It means that total mass entering the control volume during delta T minus total mass leaving the control volume during delta T equal to the net change of mass within the control volume during delta T. Okay, see, we have delta T at each of these mass. Okay, so it should be at the same delta t. Okay, so total mass entering and leaving should be known in order to calculate the net change of mass within the control volume. So to simplify, it should be written like this: m in minus m out equal to delta m control volume. Okay, so delta mcv equal to m final minus m initial. Okay, same. The change in mass of the control volume during the process. So we know, in order to calculate the change in mass delta M, okay, in a particular open system or control volume, okay, we have to deduct, okay, the mass of the final result minus with the mass of the initial mass. Okay, it can also be expressed in rate form. Okay, amount of mass flowing through a cross section per unit time. Okay, you already know where when we have a rate form, we have to use a symbol dot here. So m dot in minus m dot out equal to dmcv control volume over dt, okay, per unit time. Alright, so remember, in rate form, the symbol will the unit will be kilogram per second. Okay, let's move on. During a steady flow process, okay, so now we want to see, just now we understand about the conservation of mass principle in a control volume. So this is the conservation of mass principle equation for control volume. So let's say we want to see the mass balance equation for steady flow process. Okay, during a steady flow process, the total amount of mass contained within a control volume does not change with time. Okay, we understand just now. Okay, all of this is during delta t. Okay, however, in this steady flow process, the total amount of mass doesn't change with time. Okay, so m control volume equal to constant. Okay, even though it is open system, but when it is steady flow process, then the total amount of mass contained within a control volume doesn't change. Okay, okay, when the okay, doesn't change with time. Okay, so then the conservation of mass principle requires that the total amount of mass entering a control volume equal to the amount of mass leaving it. So let's see this equation. Okay, m dot equal to m dot. M dot in equal to m dot out. It is different with this one. Okay, m dot in minus m dot out equal delta mcv. Okay, however, this one, because it is steady flow, where the total amount of mass entering the control volume should be the same with the total amount of mass leaving the control volume. So the total mass is constant. That's why we obtain this equation dot m dot in equal to m dot out. Okay, the conservation of mass principle for general steady flow system with multiple inlet and exits will become rho 1 V1 A1 equal to rho 2 V2 A2 or rho 3 V3 A3. Okay, so we will have this equation. Okay, so when dealing with steady flow process, we are not interested in the amount of mass that flows in or out of the device over time, but we are more interested in amount of mass flowing per unit time. Okay, so we want to know the m dot. Okay, what is the m dot? So generally we have the conservation of mass principle for control volume. Okay, m in minus m out equal to delta mcv, and then we have the conservation of mass balance equation for control volume but steady flow process, means that the mass doesn't change. Okay, the mass is constant. Okay, you just have to remember about steady flow process. It is more like steady girlfriend. It doesn't change with time. Okay, so same with this, steady flow means the mass doesn't change with time. Alright. So during a steady flow process, volume flow rates are not necessarily conserved, although mass flow rates are. Okay, volume flow rates are not necessarily conserved. Okay, although mass flow rates are. Okay, so we can see it here. Okay, during a steady flow process. So now this is an example of a steady flow process where the mass, total amount of mass is constant. So we can see at m dot in, okay, mass rate m dot 1 equal to 2 kilogram per second. So now let's see on the total mass rate leaving the system. M dot 2 equal to 2 kilogram per second. So it is the same amount, means that it is steady flow process. Okay, now let's see the volume. Okay, volume flow rate. V dot 1 equal to 1.4 meter cubic per second. However, V dot 2 equal to 0.8 meter cubic per second. So as you can see here, this example, during a steady flow process, okay, mass flow rate will be constant. However, volume flow rate doesn't necessarily conserve. Alright, so many engineering devices such as nozzle, diffusers, turbines, compressors, and pumps involve a single stream, only one inlet and one outlet like this. Okay, why the volume rate at the outlet of air compressor less than at the inlet, although the mass flow rate is constant? This is one of the example is due to higher density of air at compressor at the exit. So one of the reason why volume flow rate is bigger or larger or smaller compared to the outlet. Alright. Okay. So now let's see the mass balance equation for incompressible flow. So just now, okay, we see the mass balance equation for control volume system. Then the mass balance equation for control volume system and steady flow process. So this one is mass balance for control volume system or open system, but incompressible flow. Okay, so what is incompressible flow? The conservation of mass radiation when the fluid is incompressible, usually liquid. Okay, so steady incompressible, V dot in equal to V dot out. Okay, meter cubic per second, means that the volume flow rate is constant. Okay, it is totally opposite from this one. Okay, steady flow. For steady flow, the mass flow rate is constant, but in incompressible, the volume flow rate is constant. So for single stream steady flow, above equation becomes, okay, from here we can just include the equation V dot 1 equal to V dot 2, equal to the V1 A1 equal to V2 A2. Alright, so this is the mass balance equation for incompressible flow. Okay, actually you have to see this equation. Okay, m dot 1 equal to m dot 2. So rho 1 v1 a1 equal to rho 2 v2 a2. So now let's see the incompressible. What is the meaning of incompressible flow? Incompressible means the density is constant. Okay, density is constant. So from this equation, rho 1 v1 a1 equal to rho 2 v2 a2, when the density is constant, so we can strike this out. Okay? So it becomes 0. Okay, so let's say rho 1 is 30. Okay, 30, and rho 2 also 30. Then we can strike this to so it becomes this equation v1 dot equal to v2 dot equal to v1 a1 equal to v2 a2. So no rho is in here. Okay, the density is constant because it is incompressible. Incompressible. So incompressible, the density is constant. Steady flow process, the mass is constant. Okay. All right. Okay. So now I have a exercise for you here. Air is flowing in a 0.2 meter diameter pipe at a uniform velocity of 0.1 meter per second. The temperature is 25 degree and the pressure is 150 kilopascal. Determine the mass flow rate. Okay, you can do this question and you can refer to this answer. Alright, the second question. A garden hose attached with a nozzle is used to fill a 40-liter bucket. The inner diameter of the hose is 2 centimeter and it reduces to 0.8 centimeter at the nozzle exit. If it takes 50 seconds to fill the bucket with water, determine A, the volume rate, okay, volume flow rate of water through the hose, B, the mass flow rate of water through the hose, and C, the average velocity of water at the nozzle exit. Okay, noted that the density of water is 1000 kilogram per meter cubic. Okay, or 1 kilogram per liter. So I have a answer here you can refer to, but please do it by yourself first. Alright, let's continue on the 5.2 flow work and the energy of a flowing fluid. Alright, so unlike closed system, okay, where we already understand in closed system, mass is fixed, thus no mass, only energy can cross the system boundary, okay, and volume is not fixed. Okay, so unlike closed system, control volume or open system involve mass flow across their boundaries, and some work is required to push the mass into or out of the control volume. Okay, since we already understand that in open system, both mass and energy can cross the boundary. So, in order for the mass cross the boundary, there will be some work required to push the mass into or out of the open system. Okay, for example, we have this example of a schematic of a flow work. Okay, we have a piston, imaginary piston. In order to push this mass of this proportion, okay, we are required to push with some force, with F, okay, towards this piston. Alright, in order for this piston to move to the right. Okay, so work is equal to the flow work or flow energy. The flow work relation is the same whether the fluid is pushed into or out of the control volume. Okay, usually this work is called as flow work. Okay, in the absence of acceleration, the force applied on a fluid by a piston, force applied on the piston by the fluid, okay, is the same. Alright, so now flow work and the energy of a flowing fluid. If fluid pressure P, cross-sectional A, force applied on the fluid element by the imaginary piston. Okay, this is imaginary piston. So we have the equation for force, F equal to PA. Okay, to push the entire fluid element into the control volume. Okay, to push this one into the control volume, this force must go through a distance L. Okay, like this one. In order to push this, we have to push it to one distance SL here. Thus, the work done in pushing the fluid element across the boundary will be workflow equal to F, force that is used, pressure times width of the area, force times width, distance L. So we have PAL. P pressure, A area, and L is distance. So area times distance become volume. So W flow equal to PV. W flow equal to PV. It is actually the same with the chapter 4 we discuss on the moving boundary work. So WB equal to PV, PdV. So the flow work per unit mass, W flow, small letter, W flow equal to P specific volume. P specific volume, kilojoule per kilogram. Okay, that is the flow work and the energy of a flowing fluid. Okay, a recap. Okay, total energy can be determined from two aspects, macroscopic and microscopic. What are they? Okay, in previous chapter 4, we already learned about the energy balance equation for closed system. Okay, where the total energy can be determined from two aspects, which are macroscopic and microscopic. So in macroscopic, we have potential energy and kinetic energy. In microscopic, we have internal energy. So it is micro level. Alright, next. Two forms of energy interactions associated with closed system. What are they? Two forms of energy interaction. So we have heat transfer and also work. This is two forms of energy, how energy can be transferred to a system or out of a system. And then we have write the energy balance equation for closed system. Energy balance equation for closed system is very easy. Delta E equal to E in minus E out. Alright. So now, like I said just now, so this is the answer for this question. These three questions. So first we have macroscopic. In macroscopic, we have kinetic energy and also potential energy. And then in microscopic, we have molecular level, and we call it as internal energy. And two forms of energy interaction associated with closed system is heat transfer and work. Heat transfer only happen when the driving force is temperature difference. It won't happen when there is no temperature difference, means that the temperature for the system and also the surrounding is the same. Same temperature, so no driving force. And it also won't happen when the system is in adiabatic, means that it is well insulated and a very small amount of energy can cross the system boundary. And then we have work other than temperature difference. Work other than temperature difference, the driving force. Other than temperature difference. Alright. So now this is the equation, the answer for the question just now. The energy balance for any system undergo any process, delta E equal to E in minus E out. And we also can rephrase this equation by using the heat, work, and also total internal energy. Internal energy plus delta KE, kinetic energy, plus delta potential energy. I already learned in the previous video of chapter 4. Q is 0 for adiabatic system. W is 0 where no work interaction happen in the system. And the internal energy, E mass equal to 0 for closed system. Alright, so now let's see the total energy of a flowing fluid. The total energy of a simple compressible system, a non-flowing fluid, consists of three parts: internal, kinetic, and potential energies. On a unit basis, it is unit mass basis, it is expressed as, is the same equation like this one. Internal kinetic and potential, but it is in mass, okay, mass basics. So we have internal, kinetic energy, and also potential energy. It is all written in smaller letter because it is per unit mass, okay. Then you have kilojoule per kilogram. The fluid entering or leaving a control volume possesses an additional form of energy, okay, where we call it as the flow energy. Okay, W flow equal to PV. Thus, the total energy of a flowing fluid on a unit mass basis can be expressed as, okay, so we can include the additional form of energy to this equation. Then we will get, okay, theta, the flow energy, okay, equal to PV, flow energy, or W flow, plus E. Okay, so this W flow equal plus with E. So we will get PV plus U plus kinetic energy plus potential energy. Okay, and it can rewritten like this, okay, in terms of enthalpy. Okay, the total energy. This is the theta represent total energy of a simple compressible system. Alright. So in a non-flowing fluid, okay, we have a simple equation, okay, internal, kinetic, and also potential energies. Okay, however, in flowing fluid, okay, we have flow energy, okay, W flow equal to PV plus internal plus kinetic plus potential energy. Okay. Okay, so this is just a symbol, okay, between for the equation just now that I showed you. So total energy per unit mass of flowing fluid is represented by theta, denoted with theta symbol. Total energy of a flowing fluid with mass m theta, mass flow rate m dot. Okay, so it is the same amount of energy transport. So times, okay, theta times with mass. So we will get the E mass. When a fluid stream with uniform properties is flowing at mass flow rate m dot, the rate of energy flow with that stream is m dot theta. So it's the same, but it's just in the rate term. Okay. Okay, the product m dot theta is the energy transported into control volume by mass per unit time. Okay, I have a next exercise. You can do it by yourself. Okay, and refer to the answer below. Okay, and also this one. A flow steadily in a pipe at 300 kilopascal, 77 degree and 25 meter per second at a rate of 18 kilogram per minute. Determine the diameter of the pipe, the rate of flow energy, the rate of energy transport by mass, the error involved in part C if the kinetic energy is neglected. Okay, please do it, and we have some example of the answer here. Alright, so now let's move on the energy analysis of a steady flow system. We already know, okay, what is a steady flow system previously. Okay, a steady flow process, okay, a process during which a fluid flows through a control volume steadily. Okay, we already understand steady flow. So V1 dot equal to V2 dot. A large number of engineering devices operate for long periods under the same condition, thus classified as steady flow process. Okay, steady flow device. It operates in very long periods, okay, under the same condition. So we can classify it as steady flow device or steady flow process that happens. The fluid properties can change from point to point within the control volume, but at any point, they remain constant during the entire process. Okay? It can change position. Okay? However, at any position, it remains constant. So let's see if you have the fluid properties MCV, okay, equal to 2 kilo here, and okay, after some times it change position to here, it is still 2 kilo, it doesn't change. So steady means no change with time, no intensive or extensive properties within the control volume change with time. Thus, the volume V, mass M, and the total energy E of the control volume remain constant. As a result, for steady flow system, the boundary work equal to 0 since VCV is constant. Okay, and then we have the total mass of energy entering the control volume equal to the total mass of energy leaving it. Okay, since MCV constant and ECV constant. The mass balance for a general steady flow system, okay, m dot in equal to m dot out. Okay, we learned this already. And then the mass balance for a single stream, one inlet, one outlet steady flow system is rho 1 V1 A1 equal to rho 2 V2 A2. During a steady flow process, the total energy content of a control volume remain constant, okay, ECV equal to constant. Thus, the change in the total energy of the control volume equal to 0, okay, because ECV constant. Okay, the amount of energy entering a control volume in all forms by heat, work, and mass is equal to the amount of energy leaving it. So this is the equation, the rate form of the general energy balance for steady flow process. We have E dot in minus E dot out equal to delta E, and because of this is constant, so we have E dot in equal to E dot out. Okay, so this is the equation, the total equation for steady flow system. We have the heat here, work here, and also the energy by mass, total energy by mass. So here we have the kinetic potential energy and also internal energy. Okay, we just I already summarized it here. Okay, you can refer to this equation. So in equal to out. It's the same like this one. In equal to out. So same with this one. Heat plus work plus total energy by mass. That's why m dot times with internal plus with kinetic plus with potential energy equal to the same terms but for out. So in equal to out. Alright. So here actually explain on the in detail on the definition of each terms, okay, Q dot, W dot, delta H, okay, enthalpy, delta kinetic energy, and also delta potential energy. You can read by yourself, or you can refer to the thermodynamics channel book. Alright, so last we will discuss on the some steady flow engineering devices. Okay, many engineering devices operate essentially under the same conditions for long periods of time. The component of a steam power plant, for example, operate non-stop for months before the system is shut down for maintenance. So usually, yeah, I know, I think you guys already familiar with this background, okay, where the device is operated in long hours, okay, in a long hours or months, up until months, and then at some point it will shut down for maintenance. Okay, so therefore these devices can be conveniently analyzed as steady flow devices, okay, because it is operated in very long terms of time. Okay, so that's why it is called steady flow device. Alright, for example, we have nozzle and diffusers. Okay, nozzle and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hoses. A nozzle is a device that increases the velocity of a fluid and at the expense of pressure. A diffuser is a device that increases the pressure of a fluid by slowing it down. So this is the energy balance for nozzle and diffuser. You can use this equation for nozzle and diffuser. Okay, if the question stated that it is nozzle and diffuser, so you have to use this equation of energy balance. All right. Okay, so I have another one question for you. Air at 10 degree and 80 kilopascal enters the diffuser of a jet engine steadily with a velocity of 200 meters per second. The inlet area of the diffuser is 0.4 meters squared. The air leaves the diffuser with a velocity that is very small compared with the inlet velocity. Determine the mass flow rate of the air and also the temperature of the air leaving the diffuser. Okay, I already gave the answer here. And then next we have turbines and compressor. Okay, we have turbine. Turbine that drives the electric generated in steam, gas, or hydroelectric power plants. As the fluid passes through the turbine, work is done against the blades, which are attached to the shaft. Okay? As a result, the shaft rotates and the turbine produces work. Compressors as well as pumps and fans are devices used to increase the pressure of a fluid. Work is supplied to these devices from an external source through a rotating shaft. So, a fan increases the pressure, and mainly used to mobilize a gas. A compressor is capable of compressing the gas into a very high pressure, and pumps, very much works as a compressor, except that they handle liquids instead of gases. So this is the energy balance equation for turbines and compressor. Okay, if the question stated that it is for turbine and compressor, then you can straight away use this energy balance equation. Alright, then we have throttling valves. Okay, throttling valves, here as shown in this figure, are any kind of flow restricting devices that cause a significant pressure drop in the fluid. Okay, what is the difference between a turbine and a throttling valve? Okay, the pressure drop in the fluid is often accompanied by a large drop in temperature, and for that reason, throttling devices are commonly used in refrigeration and also air conditioning application. So this is the equation for conservation of energy for throttling valves. Okay, you can refer to this equation. Internal energy plus flow energy equal to constant. Alright, then we have mixing chamber. In engineering application, the section where the mixing process takes place is commonly referred to as a mixing chamber, and this is the equation for energy balance equation for the adiabatic mixing chamber. Okay, E dot in equal to E dot out, M1 dot H1 plus M dot 2 H2 equal to M dot 3 H3. Okay, so actually, guys, if it depends on the question, if the question already stated some particular devices for the steady flow process, then you can straight away use this equation. Okay, even you don't have to analyze the equation from the start. Okay, you can just straight away use this equation. And then we have heat exchanger are devices where two moving fluid streams exchange heat without missing. Heat exchangers are widely used in various study industries and they come in various design. And this is the equation for heat exchanger. Mass and energy balance for the adiabatic heat exchanger in the figure. Okay, you can just straight away use this equation. And we also have pipe and duct flow. Okay, the transport of liquid of gases in pipes and ducts is of great importance in many engineering applications, as you know. Flow through a pipe or duct usually satisfies the steady flow condition. And this is the equation for energy balance for duct and pipe and duct flow. Okay, so that will be all for chapter 5 actually. Okay, so in this chapter, as I already explained just now, we mainly focus on the conservation of energy and also conservation of mass equations for control volume, okay, for open system. Okay, in chapter 4, we learn the energy balance equation for closed system. Okay, because only energy can penetrate, can cross the boundary. It is different with open system because open system both mass and energy can cross the boundary. So hence we learn the equations, the energy equations, energy balance equations, and also mass balance equation, okay, for this control volume. Okay, in addition, we not only learn on the energy and mass balance equation for control volume, okay, for open system, but we also learn if it is steady flow process or if it is incompressible flow, what happened with the equations. Okay, as we already learned in this chapter. Okay, the equation is different, depends on which process and depends on which flow. Okay, if it's steady flow, it is like this. If it's incompressible flow, the equation become like this. So it's different. Okay, guys, we have finished chapter 5. I will see you guys again in chapter 6. Thank you.